Good afternoon. I'm Arun Serafin, Executive Director of the Emerging Technologies Institute at the National Defense Industrial Association. Thank you for all the attendees for your support of NDIA and ETI, including our highly successful inaugural conference last week, which I hope you all attended. And thank you for joining us today for today's webinar, Interoperability 101 with Jessa Lee. This webinar is part of our Tech 101 series, where we try to distill complex technological concepts into introductory webinars with a focus on their national security impacts. Far too often, components and systems across the services are built by different companies or used by countries and allied coalitions lack basic compatibility. Sometimes they're unable to communicate with each other or support each other in combat or logistics missions, and these results in persistent obstacles for the warfighter. As the complexity of our defense systems grows, we must consider the best ways to get the most critical defense technologies to work together. When concepts of interoperability, which try to make them work together, are successfully implemented, we can achieve widespread integration of diverse kinds of platforms, enhancing situational awareness, enhancing response agility, and overall success of combat missions. This not only strengthens national security, but also reduces costs and promotes international cooperation, bolstering the collective defense capabilities of nations in an increasingly interconnected world. Today's presentation will cover the basics of this often cited but largely misunderstood concept of interoperability, including examples from everyday life, illustrating the importance of interoperability to the defense sector, and provide an overview of ongoing DoD and government activities to enhance the interoperability of U.S. forces. Some administrative remarks before we get started. First, all attendee lines are muted. Second, if you have a question during the webinar, you can submit your question in the question box in the webinar panel on the right side of your screen. We will do our best to get through all the questions during Q&A. Third, we're recording today's webinar for members unable to attend, and we'll post the recording on our YouTube site where you can view it later. Now, I'd like to introduce our speaker, Jessa Lee. Jessa Lee is the CTO of Apogee Research, where her work is focused on developing national security and intelligence community capabilities, including systems integration, distributed tracking and data fusion, electronic warfare, command and control, and distributed cyber networking operations. She holds a bachelor's degree in physics and a master's degree in electrical engineering, both from Stanford University. Thanks for joining us, Jessa, and appreciate you bringing your insights and expertise to our audience, and I'll turn it over to you for the presentation.
Thanks, Arun, and thanks to all of you for being here today. So now I'm going to sort of jump into sort of interoperability, and hopefully you find this useful. So I'm going to start with the question of what is interoperability. So interoperability, as Arun referred to, is the ability of systems to function together. Colloquially, we often talk about the ability of systems to talk with one another, obviously in a way where the sides understand each other. We often hear this in the context of military systems, but interoperability actually applies much more broadly. So if we take a look at this picture on the left, we have sort of a mission capability and operational capability. And in this capability, we have all these different platforms, and we want them to be able to communicate. There's satellites, there's a variety of planes. There's also sort of some weapons, there's a ship, as well as sort of a distributed C2 perhaps. And what we can see here is we want these platforms.
Jessa, sorry to interrupt. You need to share your slides.
Oh, I'm so sorry. Were they not being shared? My apologies. Okay, are my slides shared now?
Good to go.
Great, thank you so much there. So I'll sort of start over. I should say again, so interoperability is the ability of systems to talk with each other. We often hear about this sort of in the context of military systems. And so you can see the sort of operational capability in this picture in the middle left. We have all these platforms and we want them to be able to communicate and exchange information. Perhaps it's sensor data, perhaps there's tracks, perhaps there's sort of targeting data. There's lots of things that you want to be able to coordinate. This picture makes this idea of systems and integrated systems and interoperability quite clear, but it actually turns out if we open up the platforms themselves, inside the platforms looks exactly the same. So if you take any complex cyber physical system today and you open it up, what you'll find is there's a bunch of different subsystems that have been integrated together. You might have, for example, sensors and trackers, displays, different components, and these components all need to, they're built by different teams, and they all need to be able to communicate to realize the full functionality. So now the question is, why does interoperability matter? And I think Arun did a really nice job of summarizing some of the things, the reasons it's important as an intro, but I'll sort of list 3 here explicitly, just sort of frame this presentation. The first is the lack of interoperability is showing up in your daily life. It's all around us at this point because we have so many digital systems as part of our daily life. Another reason is that interoperability can actually help us develop new platforms more efficiently. So if you look at this picture on the right, you can see that the cost of fighter jets over time has actually increased exponentially, and this is a per unit cost. And as you can see, exponential growth of price is never a good thing. And so one of the things that I believe interoperability can help us with is to actually build platforms more efficiently and more cost effectively going forward. So I'll come back to that in a little bit. It's a little bit of a teaser. And another reason that I think it's important for the DO right now is that Mosaic Warfare actually requires rapid instantiation of interoperability as well. Great. So what are some examples of interoperability or the lack of interoperability that you might have noticed in your daily life? You might have been part of a text group where you have Apple users and Android users, and you might have noticed that iMessage works differently when there's an Android user in the group chat. Why is this? Well, there's an interoperability problem. The Android and the Apple standards don't actually operate cleanly. Perhaps you got a new phone and you found that it didn't work as well with your current car. If you've gone to the doctor, perhaps the hospital, as well as sort of your local doctor, perhaps you've had trouble transferring health data records back and forth. This is something that's always a little bit surprising, I think, when you first experience it, because as a country, we've invested enormous resources in electronic health records. It seems like you should be able to send the data back and forth seamlessly. Unfortunately, this isn't the case. And one of the reasons it doesn't work the way you'd like it to is a lack of interoperability. The list goes on and on. Perhaps you bought a home alarm system and found you could only buy that specific vendor's hardware because the alarm doesn't interoperate with the hardware from other vendors. Or perhaps you have an old printer with a new computer, the driver doesn't work, you're not able to use the printer, even though it's still a perfectly good printer. So mechanical systems also have interoperability challenges, and they use adapters. And I'll use this sort of as an example, and it turns out we can do the same thing for software, which I'll talk about in a moment. So if you've traveled to Asia or Europe, perhaps you've used a plug adapter that enables you to plug your US electronics into an outlet with a different form factor. Sometimes there's also voltage conversion depending on where you've traveled and whether or not the device can handle it natively. You might also have used a USB-C or Lightning adapter to allow you to plug your old school audio headphones into your phone, since they've now removed audio jacks from most of those models. So what does this look like for software? So I'm going to sort of develop a simple example here. So we're going to use simple messages describing vehicle models. So these messages might be used by, say, cooperating auto shops to share data about the models of cars that they service. We can imagine that different auto shops are going to have different systems, and they might have different data messages or data formats that they use internally. So I've picked sort of M1 and M2 as 2 examples here. So if we look at these messages, they describe, again, vehicle models. And so they have make, model, and tank size, as well as engine size. M1 has these fields sort of ordered, as you see on the right. And M2 has the same information, but it's in a slightly different order. And what we can see is that the tank size is measured in gallons instead of liters. And so the interoperability challenge is, how do we get these messages to translate so these systems can talk? So how are we going to make this work? Well, the approach we're going to take is to create interoperability between subsystems using glueware. And the idea here is that the glueware is translates the mess between the message formats. And so it's going to take the bytes of message 1 and it's going to convert them to the format expected by the subsystem that uses message 2. And this transformation is going to be specific to the source and the destination message pair, which is going to allow us to make it small and fast at runtime so we can do these conversions really quickly. So to implement this for message 1 and message 2, we're going to take the make and we're going to map it to the sort of the make and message 2. We're going to do the same thing for the model, and then things get a little bit more interesting with tank size and engine size. We actually need to switch the order of the field, sort of swap bytes, the byte order, so that the data is in the format that the systems expect. In addition, when we do this mapping for tank size, we actually have to do a unit conversion. So we convert the liters to gallons to make sure, again, that the bytes have the meaning that's expected when they're read by the destination system. Great. So now what happens when we add a third system that uses the same information but has a different record type, M3? Well, we can see this record type M3 up here. We're going to go ahead and do the same thing that we did before, which is we're going to add transforms to allow interoperability with M1 and M2, again, so these different systems can talk. And as you can see, we now need to add transforms not just to one message, but to two different message types. And we've done the mapping with the conversion in terms of the swapping of the order when necessary, as well as the unit conversion. Now, the thing to note here is there is a better way, and we'll come back to it, but I'll get there in a second. So this approach, we can extend it now to another message type, which I'll call M4. So now imagine you have this system, M4, and it has the same information, but it adds information about engine type. Well, if we want to create interoperability, we can take the same approach, and we're going to keep adding more transforms. What's nice about this approach is that when we have M4, we can actually just drop engine type when we transform to M1, M2, and M3. This enables this message with additional information to still talk to systems that don't use that information without any problem. And on the reverse transform, M1, M2, M3 to M4, we can imagine filling that in with a missing or other value to allow M4, if the information is not required, to still receive the partial information from encoded in M1, M2, and M3. So while this gives us sort of backward compatibility, which is really nice, you can also start to see that this sort of network of transforms is getting really messy. So what happens when we add a fifth system, M5, that also has an engine type information? Well, we're going to take the same approach we took before. We're going to keep adding transforms. And so when we add M5, we're going to add transforms to M1, M2, M3, and M4. And as you can see in this picture, it's starting to get really quite busy. The thing that's nice about these transforms, though, is they can transfer the information that's available. So when M5 is converted to M1, M2, or M3, we drop that engine type information. But when M5 is converted to M4, we can preserve that information, which means that systems using M4 and M5 can exchange that information because it's available. But M5 can also send information to older systems, M1 and 2 and 3 in this case, that don't contain that information. So we can sort of summarize where we're at, which is that local standards are flexible. When M4 and M5 add additional information, we were able to share it between M4 and M5 without issue, while also downcasting, removing that information to allow interoperability with systems using M1, M2, and M3 as well. The problem we saw was in the messiness of the graph that you probably observed with me. So if we think about when we added M2, we had two transforms to add to and from M1. When we added M3, there were 4 transforms to and from M1 and M2. When we added M4, there were 6 transforms we had to add to and from M1, M2, and M3, and so on and so forth. And again, these are the number of transforms we have to add. And so what you can see is that as the number of messages increases, the amount of work that you have to do to add another message or another subsystem that uses that message actually increases. And this is really not how we want to spend our engineering hours. If you talk to an engineer, they might tell you that they might describe this to you as the total number of transforms grows quadratically, as you can see in the plot on the bottom left. But again, as the number of messages increases, there's more work to do for every message you add. This is not a good place to be. So now the question we can ask is there a different approach that we can take? Is there another way to do this? So now I want to talk about this idea of global standards, which is to say, what if instead of transforming directly between messages, all transforms were to and from a single shared global standard? Well, in this case, what we're going to do is we're going to take M1, and instead of mapping it directly to M2 as we did before, we're going to map it to this global standard. Similarly, if we had M2, we're going to map it not directly to M1, but we're going to map it to this global standard. And if we want to get through M1 and M2, we're now going to accomplish this by composing these transforms, by effectively chaining them. So we're going to go from M1 to the global standard and the global standard to M2 to allow us to get from M1 to M2. And we can do the same thing in reverse. And I want to step back and I want to say sort of global standards are often the way that people think about interoperability conceptually. There's a common message format and you can both convert to that, and it makes it easy to get between the messages that you care about. The problem with global standards is actually not this idea of composition or this idea of sort of transforming to and from a known format. Instead, the problem is how do you actually pick this global standard? What is the right message to put in the middle? And I'll come back to this idea in a little bit. I want to be sort of a little bit further on in this example, because you'll see how it starts to become a problem. So what's nice about global standards is they make it easy to add new messages. So when we go ahead and we add a third system that uses M3, what happens? How do we do this? Well, we add transforms again to and from the global standard. And what you can see here is we're starting to get a much cleaner graph. Whereas with the with the local standards, we had to map from M1 directly to M2 as well as to, directly to M1 as well as to M2. With the global standard, we only need to write transforms to and from this global standard. When we add a fourth system using M4, you can see that we do the same thing again. So we take the M4 message, we map to and from the global standard, and now we're able to achieve interoperability with the existing systems. And again, just to be explicit here, if we want to go from M4 to M1, we're going to compose the transforms that go from M4 to the global with the transform that goes from the global to M1 to allow us to realize that chain. And we can do the same between any pair of messages in this graph. And so what you can see is that global standards are really nice because the total number of transforms grows linearly. For each message that we add, we only need to add those two transforms to and from the global standard. And so this gives us much better scalability than we saw with the local standard previously. So the question is, what's wrong with global standards? And the answer is that global standards aren't flexible. So there are lots of global standards. And I think XKCD says it perfectly here, which is to start with a situation, there's 14 competing global standards. Person says 14 ridiculous, we need one universal standard that covers all of them. And as a result, we soon have 15 competing global standards. So how does this play out? Now I'd like to go back to this M5 example, and you can sort of see this for yourself. So what happens when you add this fifth system that uses the message M5 in this sort of global standard approach that we're taking? Well, the interoperability, we're going to take this M5 message, we're going to write transforms to and from the standard message, and this is going to give us interoperability through composition by chaining these transforms to all the existing messages. So if we want to go from M5 to M1, we can again compose this transform that goes from M5 to the global standard, with the transform that goes from the global standard to M1 to allow us to sort of get between the nodes. The problem that comes up is what happens when you want to have M5 convert to M4 and vice versa. Well, I can compose the transforms. We're going to go M5 to the global and then the global to M4. But the problem is the global doesn't contain that engine type information. So even though M4 and M5 both contain engine type, the global doesn't allow those systems, those messages to exchange that information. And so there's no way for us to use this global and get all of the data that we have available to be shared between those messages, which is not great. So now we end up now we start to see the problem with global standards. And they really leave us in a bad place where we have two bad options. One is we can decide, well, we don't care. We're just going to drop engine type. It doesn't matter. We're not going to support any capabilities. And this is just not practical in the DoD, where people are continually inventing new technologies, and we want to make sure that the latest technologies are available for our operational capabilities. The other option is to change the global standard. But if you change the global standard, it's no longer global, and it's also really expensive to do. Because if you want to change the global, you now have to change all of the existing transforms. So if I wanted to add, in this example, engine type to the global, I have to change the transforms for M1, M2, and M3 as well. So just to summarize what we've seen so far, local standards are flexible. They allow the exchange of information between M4, of engine type information, between M4 and M5 when it became available, but they're not scalable. We had this N squared problem where each additional message became more and more expensive to add. Global standards were scalable. We had this sort of nice sort of star-shaped graph here with everything radiating out from this sort of central global node. But the problem is that they aren't flexible they didn't allow that engine type information to be exchanged between M4 and M5. So the question then is, it looks like there's a trade between flexibility and scalability. Is this a real trade, or is this something where actually it's possible to get both? And perhaps unsurprisingly, given that I'm giving you this presentation, it turns out that there is a better answer. Incremental standards actually will give you scalability and flexibility simultaneously. So what's the inspiration for incremental standards? Well, if we look at global standards, what we can realize is the scalability of global standards came not from the fact that there was a global node in the middle, but from the fact that we used the idea of composition. We chained transforms to go from M1 to M to anywhere else. We chain the M1 to global with the global to the destination node. And so the inspiration for incremental standards is, what if we were to use this idea of composition, but do it without the actual need for a global standard? Can we get the scalability of globals via this composition mechanism without the lack of flexibility that's imposed by having a global standard node? So now I'm actually going to sort of work through this example with incremental standards to hopefully help you understand why incremental standards are able to give us the best of both worlds. So the approach with incremental standards is to create transforms between messages, and then we're going to compose these transforms just as we did with globals. So if we start with the simple example that we had at the beginning, we have M1, again, this sort of same car model data, and M2 as before. And to get started with incremental standards, we're going to write a transform directly between these nodes, just as we did for local standards. We're going to map the make to the make, the model to the model, and tank size and engine size similarly, switching the order and doing the unit conversion as necessary. So now what happens when we add that third system that uses the record type M3? Well, with incremental standards, instead of mapping directly to both M1 and M2, we're just going to add transforms to one existing message. In this case, we're going to pick M2. So when we write this transform, we can write the transform directly between M3 and M2. If you want to convert for M2, you can use the transform just on its own. But if you want to convert to M1, you can use this transform in composition. So to go from M3 to M1, we can go from M3 to M2 and M2 to M1. And the result is a transform that'll sort of take us between M3 and M1 using that composition of two transforms now. Now what happens when we add the fourth node that uses message format M4? Well, we're going to keep adding transforms, but we're going to add transforms just to one existing message. In this case, we're going to choose M3. And again, we can convert to other message formats by composing transforms, by chaining them together. So we can go around the loop. We can go from M1 to M3. If we want to go to M2, we can add on this additional M3 to M2 transform. And if we want to get to M1, we can do so by adding the additional transform that takes us from M2 to M1. So now where do we end up with sort of scalability and flexibility? Well, when we add M5, the message that also has engine type information, we can go ahead and take this message format and we can hook it into M4. What's really nice about this transform is it allows us to have a direct transform between M4 and M5, which enables us to exchange that engine type information because both messages have it available. If we want to go from M5 to any other node, we can do so by composing the transforms that are already in this graph, going from M4 to M3, M3 to M2, and M3 to M1 if we want to get all the way to that M1 node. One thing to again mention here is just that these transforms from the transform from M4 to M3 is going to drop the engine type information because it's not present in M3. And so what we can see is we're able to exchange the information when it's available, but also to downcast, to drop that engine type information when it's not present in the messages to allow us backward compatibility with existing systems. And so you can see looking at this that we have flexibility. We're able to accommodate the engine type information, but we also have a relatively clean graph. We haven't had to write that many transforms. And as you can see in the plot on the bottom left, incremental standards like global standards also grow linearly. They're much more efficient than the local standards, which grew quadratically. So now I can bring us back to this slide here, which is to summarize sort of where we ended up. When we started, we had this this parent trade between flexibility and scalability, with local standards being flexible but not scalable, global standards being scalable but not flexible. And what we found with incremental standards is we can get flexibility and scalability simultaneously. And again, we did this by using this idea of composition without actually creating a global standard, which is what caused us to lose flexibility with that global standard. And one of the things I want to point out here is that perhaps you're wondering, well, why are global standards inflexible? What makes them so hard? And the answer is that in order to create a global standard, everyone has to agree upon the standard. But if you think about the variety of organizations, if you think about the variety of technologies that they're developing, everybody has different needs and different use cases. And so getting everyone to agree is really hard. Practically, what that means is that global standard messages tend to get really big. They have all of the options that anyone could possibly need. Well, that's great. It seems like, well, if you can cover all the bases, maybe that's a good place to be. The problem with that approach is not everyone has everything. So now you have a message that's not only giant, it also has lots of optional structure. There's lots of things that might be present or might not be present, depending on which some systems are using the message. The result of this is that you have this highly optional structure, this message with this highly optional structure, and you can end up with having two systems that use the same message that can't interoperate because the optionals required by one system aren't provided by the other system. And so these global nodes, while they seem really like a nice idea sort of in theory, end up never working in practice. The other thing to point out is that when I showed the sort of previous slide, it probably seemed like it was just a trade between flexibility and scalability. But it turns out it's actually a trade between scalability and every other thing you care about. Scalability drives costs, so it makes sense that people care about scalability. And sometimes, perhaps in the commercial world, when you really care about scalability, you're willing to sacrifice things like flexibility and performance. The problem in the DoD is that the DoD also needs scalability, but we also need performance. A lot of times these systems are going to run on devices with limited compute. They might live sort of at the edge. And so we can't just assume that performance doesn't matter. We also need flexibility because people are continually developing new technologies. People are continually developing new technologies, and we want to be able to make those available for our operational capabilities. So now what I'd like to do is to walk you through this argument in terms of performance to help you understand why it's a trade between scalability, not just scalability and flexibility, but scalability and everything else. So if I look at the local standards here, local standards are performant because I can create point-to-point transforms that are hand optimized between each of the message types. As we saw before, they're not scalable because I have all of the pairwise connections, making this star and this pentagon as you see on the page. Global standards are scalable, as we saw before, but they're not performant. And the reason they're not performant goes back to that global standard message that I just described, where you have this large message with lots of optionals. And it turns out because you have this highly optional structure, you can't figure out what you're going to have and not have before runtime, compile time. You have to do it at runtime. And what that means is that when you're actually running your code, you have this large, highly optional message, and it's really hard to get good performance. Incremental standards, by contrast, are going to give you the best of both worlds. Now, I'm guessing you're looking at this picture and you're thinking, if I want to go from M1 to M5, I have to compose all the way around the ring. How on earth can that be performant? And the answer is that incremental standards give you two things. The first is they give you the ability to be specific with your messages. Instead of having giant messages with lots of optional structure, you can make these messages have just the information that is necessary and nothing else. The other thing you can do with incremental standards is the relationship between these messages, the transformations that we been describing, those can be expressed in a limited programming language that's easy to analyze. These are often called sub-Turing complete DSLs. What that means is you're able to take these transforms and actually chain them together. And when you chain them together, you can, at compile time, you can actually take all that code and you can effectively squish it down and optimize it. As a result, instead of actually having to realize the intermediate messages, M2, M3, and M4, if you're going from M1 to M5, you can actually take those intermediates and you can effectively squish and optimize them out. The result is a really small transform that's efficient and is both small in terms of its footprint and can run very fast at runtime. And again, as we discussed before, you get scalability because we can compose these transforms so so the amount of work to add a new message doesn't increase as the number of messages in the graph increases. One thing that's worth pointing out here is that the NDAA in 2021, Section 804, actually established new requirements for modular systems, and it recognized some of the limitations associated with some of our existing approaches and opened the door to allow supporting things like incremental standards. And so I actually copied the law here. And if you go ahead and look at Section B, what you can see, and so what this does is actually describe sort of what is a modular open system approach. And in bullet A, we see that it's a system that employs a modular design that uses modular system interfaces between major systems. And bullet point B is really the part that I think is interesting, where we talk about the fact that it's subject to verification to ensure that the relevant modular system interfaces. Well, how are we allowed to do that now? Well, there's actually two ways. The first is you can comply with available and suitable, widely supported consensus-based standards. These are the global standards that we discussed previously. But sub-bullet 2 offers another approach, which is to say that you can describe the interfaces by providing three things. The first is software-defined interfaces, syntax, and properties, specifically governing how the values are passed and received between major subsystems and components. And what this is saying is you need to know what the messages are. You need to have that definition of M1, M2, M3, M4, M5 in our example to say what kind of messages are being sent and received by the subsystems. The second thing that's required is a machine-readable definition of the relationship between the delivered interfaces and existing common standards or interfaces. And what this is saying is you need a way to relate the messages that your subsystem sends to existing subsystems or other common standards. These are the transforms that we described between the messages. And here they suggest that they should be, well, they say that they should be checked into a department interface repositories, which is to say we want these to be in a form that other people can check them out and use them. Other people can compose them with their transforms to reach other different systems that are in this graph. The third thing you have to provide is documentation with functional descriptions of the software-defined interfaces, which is to say you need documentation saying what your subsystem actually does. And so this is a really nice description of the information that seems like a logical thing to provide with your subsystem, but I also want to point out that it's compatible with incremental standards. As we saw, you need the field definitions, the relationship between the different fields, and then documentation against saying what they are. So now I want to step back and I want to talk about this idea of interoperability and sort of get back to the big picture and sort of ask the question, so I've talked a lot about sort of how interoperability can be implemented, but why do we care? And I think an easy example to talk about is the Internet of Things. So the Internet of Things is going to have all kinds of devices in it. I think we've heard about it for a while. The reality, as we've seen, is that getting interoperability is hard. So you've got everything from cameras and thermostats and phones to refrigerators, cars, perhaps parking lot signs. To get all this stuff to integrate to work together, you need flexibility and scalability. You're going to have new devices that are being created all the time. And obviously, there's going to be a lot of them. And it turns out that practically what we've seen is industry has been trying really hard to come up with a standard to make the Internet of Things, even just the home Internet of Things, work. The standard that's being developed by a lot of the big players, so the Apples and the Googles of the world, is called Matter. And there was recently an article that was published by Stacy, who wrote a blog on the Internet of Things for many years saying, Matter's problem isn't the standard, it's the vendors. Well, given what we've seen, I think it's actually the fact that they're trying to create a global standard. When you try to get all of these different entities to agree on something, the reality is they all have different devices, they have different use cases. Getting that agreement is really hard. In fact, it's pretty much impossible. And so when that standard doesn't quite do what the players want it to do, they start to take sort of escape hatches. They start to use either parts of the standard that aren't fully they start to use escape hashes because they need a functionality that's not in the standards, and so they find workarounds. And so what you can see here is that Matter, which has been sort of rolled out in the last sort of year or so, it's not sort of fulfilling the promise that people thought it would, and people are starting to ask this question of why. And I would argue it goes all the way back to the fact that we're trying to come up with a global standard. We've tried to create one set of things that will do everything, despite the fact that we have this highly heterogeneous ecosystem that makes that kind of agreement hard. So next, I want to talk about this question of why does the DoD care about interoperability? And I think it goes beyond just sort of the question of getting devices to interoperate at a sort of local level. I think there are actually compounding effects. So specifically, the DoD has long assumed that homogeneous fixed configuration weapon systems are the only way to meet the goals of a superior military force. Well, the implication of this is that these platforms have to last a really long time. And so the requirements have to meet a similar time horizon. But meeting requirements that are 30 years out with today's technology is really hard. And the result is that you have the best design possible 20 to 30-year-old technology because you have to make the design today. You have to implement it, you have to make the design today, you have to implement it, and then it's not going to fly for many years. And so you end up with a plane that's actually using old technology when it gets to its initial flight. This is something that's showing up not just sort of in the engineering labs, but actually at the level of the national budget. So I sort of showed this chart earlier, and what it shows is that the cost of fighter jets for the per unit cost has increased exponentially over time. And Norman Augustine was the United States Undersecretary of the Army in the 70s. He also served as the CEO and chairman of Lockheed Martin. And he sort of wrote a set of laws that were very much tongue in cheek, but he made the initial version of this plot going up to 1983. And then he wrote, in the year 2054, the entire defense budget will purchase just one tactical aircraft. So he's taking this trend to its illogical conclusion. What we can see is that past 1983, projection has held for quite a while. The Joint Strike Fighter has done slightly better. This plot was produced in 2010, so the data is a little bit out of date, but still the costs are incredibly large. So this approach seems like it's pretty expensive, and it's worth highlighting that the exponential increase in price has happened despite the fact that with Moore's law, the amount of compute has actually increased exponentially. The cost of computation has gone down, and yet the cost of these fighter jets is continuing to increase exponentially. The other things that happens when you design capabilities this way is that the timeline to deliver the capabilities has gone up and up over time. So if we take a look at this plot, what you can see is that, the time to deliver aircraft was about 5 years until 1975 or so. Since then, it's increased fairly linearly. Both the F-22, it got up to 19.1 years from contract to the initial operational flight, operational capability, and with the F-35, we're well beyond that. So now let's ask the question, what if we could rapidly integrate new technologies into existing platforms? Well, we could create systems that are the best at initial operation, and they can be upgraded so they continue to be the best over time. In this approach, the initial requirements wouldn't need to be as aggressive because the capabilities will continue to be upgraded. And this means that the requirements can be more easily met with today's technology. The result is faster initial development and deployment. And I think it's worth pointing out here that this means that you get a better capability at every point in time. One example we can point out here is that with the F-22, several electronic components were obsolete before the initial operational capability, which effectively meant that we were buying technology that consumers were no longer using because it was considered too old to support an airplane that wasn't yet even in use. And so if instead we could upgrade these capabilities, we would have a better capability today, also because we could continue to upgrade the capabilities on the plane. Whereas with the F-22, that's actually extremely difficult. The other reason that interoperability is so important is perhaps you've heard about Mosaic Warfare, which is a new strategy that provides a more dynamic vision for warfare. And the idea here is that instead of acquiring integrated fixed capabilities, which is what we do today, what if we were to shift to acquiring component systems and then to create operational capabilities by composing the systems to meet mission needs? Well, this would give us a much more sort of dynamic, recomposable set of capabilities. And it has a lot of advantages because right now, as we saw in the previous slide, we make platforms. They take a really long time for us to develop them. And the result of that is that we create complex capabilities. They're integrated. They take decades for us to create. But they're only one point in space. And what that means is that our adversary can counter the instance that we created relatively easily. If instead we were to acquire components, we can then recompose those pieces. There's many possible different capabilities we can create. As a result, it'd be much harder for our adversaries to counter our technologies and our capabilities. But getting to Mosaic Warfare isn't easy. In order to do that, there are new technical challenges that need to be tackled. Specifically, Mosaic Warfare creates a need for scalable on-demand interoperability between highly heterogeneous systems. So this isn't just a matter of getting new systems that are going to talk to each other. This is a matter of trying to figure out how do we get our new systems to talk with our old systems. We need multiple generations of technology developed over decades to be able to communicate and integrate in order to be able to realize this vision. We also need new tools to enable rapid composition of rapid instantiation of new capabilities, which is to say, given a desired mission capability, how do you actually instantiate that capability using the parts that you have? So we can really think about this as, if you think back to sort of the Apollo 13 problem, which is you had sort of square peg round hole, how do you actually take the components that you have? It was dramatized in the movie, probably don't need to sort of throw them all on the table, but conceptually, how do you take the components that you have and then figure out how to turn them into an operational mission capability like the one that you see on the right? And the real challenge here is that the systems engineering view won't work for Mosaic Warfare. With systems engineering, you start with the concept of operations, then you get requirements and architecture, then a detailed design, implementation, and then you sort of pop back up with integration, test and verification, system V&V, and operation maintenance. And so we're sort of starting at the top, we're going all the way down, and then we're coming all the way back up. But with systems engineering, we have a bunch of components. We need to figure out how to compose them. We need a new process to be able to do this. And I think the specific thing to call out here is that systems engineering, this V, doesn't consider existing capabilities until after a detailed design is complete. And if you do the detailed design first, inevitably the requirements that you come up with aren't going to match the capabilities that you already have. And so it's not an easy process to sort of modify or to apply to this systems of systems engineering approach. So instead, we need a process, which we'll call systems of systems engineering, that allows us to consider these inputs as these existing components as first-class inputs, that considers the technologies that we already have available as it figures out how to create this detailed design. So to do this, there's actually a systems of systems engineering process, which is an iterative process for developing these compositional systems. And I know this is quite a picture, so I'll sort of walk you through it here, which is to say you start with the mission capability, you get to a desired mission capability, then you identify the subsystems, as you can see that we're considering the components that we have right from the beginning. Once you've identified these systems, you can analyze them, characterize them, and this, along with the mission capability, is going to feed into the architecture definition, which is here. From there, you can create an MVP and a running prototype. And then you can sort of run around the sort of iteration and development chain, which is to say you're going to identify missing features, come up with features, prioritize them, develop them, and then iteratively expand your capability. The output of this is actually the requirements met, from which you can create releases. You can feed that information back if you want to sort of improve your analysis of the subsystems. You can also create releases for testing with your partner organizations. And obviously, as you identify bugs and deficiencies, you're going to put that back into your development cycle. So the two things that I think are really important to sort of take away from this picture is that systems of systems engineering uses the systems you have as sort of first-class inputs. So they're here really early on in this process. And then the second thing is the requirements are how the engineering team documents how they are meeting the capabilities. Instead of coming up with a detailed set of design and requirements up front, it's actually sort of part of our iterative process that sort of pops out as you sort of develop your capability. The other thing that's, I think, is important to highlight here is that the systems of systems engineering approach meets the requirement of DoD Instruction 5087, which was about the acquisition of software. Specifically, this instruction from the DoD stated that a rapid iterative approach to software development reduces costs, technical obsolescence, and acquisition risk. And you can see one of the key pictures here on the left. The idea is that we need iterative development that allows us to sort of iteratively develop the capability, assessing value, testing, and ensuring that it's actually meeting our operational needs. perhaps I should have marked this sort of more clearly here, but if you follow these errors, what you can see is there's many iterative sort of processes built into this systems of systems engineering approach. On the top right here, you sort of have the iterative development loop, the sort of requirements forms a little bit of a loop as well. And we also have this larger cycle where we're pushing bugs and feature requests back into the system, allowing for iterative both refinement as well as expansion of the capabilities that we have. So with that, I want to wrap things up and just say in summary, I know this is a lot. So what have we talked about today? Well, we've talked about the fact that interoperability is the ability of systems to talk in ways that they understand each other. We've talked about the fact that incremental standards are scalable and flexible because they use composition without having the lack of flexibility created by a global standard. We've also talked about some of the implications for why interoperability is so important. The hypothesis that the ability to rapidly integrate new technologies into existing platforms can help us deliver more new capabilities faster with better capabilities at every point in time, and hopefully for fewer dollars as well. Mosaic Warfare also requires on-demand interoperability, and the systems of system engineering workflow provides an iterative way for us to develop these capabilities and actually hopefully be able to realize the vision of Mosaic Warfare as well. Great. So that I'd like to say thank you, and I'll hand it back to Arun. Thank you all for coming today.
Thanks, Jessa, for that great presentation. The questions came in. If any of the attendees has questions, please enter them into the question box on the side of your screen, and we'll try to get to as many as we can with the time remaining. Let me just, there's a nice long list here. Let me try one. Early on in the talk, you talked about glueware. But the example you gave was a commercial automotive example. Can you give us an example of the kind of metrics or data values that would go into the glueware for a defense mission?
Sure. Yeah. So the glueware is really about transforming the message formats that are used by the subsystems that are the systems that are communicating. And so this really just depends on the systems that you're interested in integrating. So if you're looking at radars, it might be sort of the radar scan data, and you can imagine, perhaps you need to change coordinates, perhaps you need to change units, something like that. It could also be tracks. It could be really anything that's being sent and received by your system. So video data, you can look, the Internet of Things is obviously another commercial example, but, to use a really simple example, you can imagine that there's a message to turn a light switch on, a light on and off. That could be the data that's in the field that's being sent and back and forth between your light bulb and the controller that's actually controlling.
You talked about incremental standards as a possible way out of the complexity here. What's an example of, could you walk us through a DoD example of an incremental standard? Right,
so incremental standards is not, it's actually an approach to creating interoperability. It's not sort of a standard itself. And sort of, I think the thing to probably highlight here is incremental standards were actually developed under a DARPA effort. There was a program called SOSITE that originally sort of helped create this work. Incremental standards are implemented in a tool chain that's called Stitches, which is available on a website called stitches.mil if you're interested. It's released under a license that is both distro A and sort of an MIT open source license. So you're welcome to take it with it and do what you want with it. But the idea here is that incremental standards are not, it's not a standard, it's an approach for creating interoperability between whatever messages your systems happen to use.
Another question, in general, developing standards, is it something that's best done by government or industry or both when it comes to defense?
Right. So I would actually argue that the idea of coming up with standards is not the approach that we should be taking. And instead, we should be asking each of the systems that use data to specify that the data that they use in a clear sort of message specification, as we saw actually sort of in that sort of in the NDAA law that I referenced. So instead of creating standards, what we want is systems to be specific and clear about the information that we're using. And then I think what we'll see over time is that they're often emergent standards. So when people come up with data messages that work well, people often decide to either use them or link into them because they're a useful, clear reference point. So rather than coming up with standards ahead of time, I would argue that we should wait for standards to emerge based on the technologies that we're using, the systems that we're using, and the data that they're sending back and forth.
How could you talk a little bit about how incremental standard approaches would either support or cause problems for MOSA approaches?
So I probably should have an answer to this. I don't think I have as clear an answer as I should. What I will say is that incremental standards don't meet the, like, if you need to have a common standard, obviously they don't have a common standard. But what we found is that they are useful for integrating messages of all types, including different messages, or including messages between different global standards. So one of the things we've actually done is most global standards have multiple versions of them internally. And so we've used incremental standards to actually to create interoperability between the different versions of the global standard itself.
A couple of questions on Mosaic Warfare. What's the difference between what you described as Mosaic Warfare and what the department sometimes calls combined JADC2?
So the JADC2 is Joint All-Domain Command and Control, I believe. So I think JADC2 is I would describe it as a Mosaic Warfare style desire for sort of interoperability between systems. I think Mosaic Warfare's approach, my understanding is that JADC2 is a specific effort, but I think the goal of the two is to create these sort of integrated capabilities that allow multiple different systems that were not designed to work to each other to communicate effectively to build better capabilities.
Broader question, what's your sense of how interoperability efforts are working internationally with coalition partners? What, in your view, do we need to do better with our allies and partners to promote interoperability?
Yeah. And so I think there's sort of two questions here. There's sort of there's a non-technical policy part, and then there's a technical sort of part. And I'll sort of focus on that second part, in part because I think that it sort of unlocks degrees of freedom for sort of the non-technical discussions. But I think that the starting point from my perspective is that instead of focusing on creating standards to create interoperability, instead we should think about what information we want to exchange with them, and then sort of and then start to build interoperability on those messages specifically. So I think that the effort to create a global standard actually makes it more difficult to achieve interoperability because those messages seem to be so large, they're ambiguous, but also because it takes so much work and coordination to create them up front. So if we instead just sort of create interoperability on local instances using sort of this incremental approach, I think we'll have a much more incremental approach to be able to create interoperability that will actually get us there faster.
And just my own follow-up, is that incremental approach then at the local level then also more cost-effective at the program level?
So I would argue that the answer is yes. One of the things that we've actually seen using incremental standards is that people, from a technical standpoint, the inspiration was that we get scalability and flexibility simultaneously. What we actually find with these tool chains is that they're faster when you're doing the first implementation as well. And I think this is a lot like creating specific programming languages or application-specific tooling. It turns out when you have good tools for interoperability, they actually help your engineers to go faster. You get better results more quickly.
A couple of questions on things that make everything hard. How do budget constraints and acquisition processes impact efforts to achieve interoperability in military systems? In fact, interoperability is sort of written into some requirements, right? There's a KPP for net ready. There's a net ready KPP that's applied on all systems. So what's your sense of budget constraints and current acquisition processes and whether they're helpful or hurtful to interoperability?
Yeah, I'm not sure that I have the best answer on this, but I think what I'll say from a technical standpoint is that when people predicate interoperability on having a global standard, it induces a large upfront cost that means that you have to make this enormous investment with the hope that you'll get interoperability later. When you move away from global standards and you instead move to something like incremental standards, it allows you to create interoperability with the systems that you need to interoperate with practically to achieve the goals of your specific effort, and then allows you to sort of incrementally build out from there. And so from a budget standpoint, if we move away from this idea that we're going to create consensus first and then just instead just sort of jump in, I think it creates a much less expensive, actually more efficient path for interoperability that will get us there faster.
Another policy issue, how much of military interoperability concerns are technical and how many are caused by issues like technical data rights, IP control?
So I think that there's a sort of combination. I think one of the things that I believe the NDA actually did was that it said that the government actually gets access to your interfaces, saying we should have fewer proprietary interfaces. If the government buys the system, it should have access to the interfaces because we bought the system. And so I think hopefully that will over time make some of the proprietary data issues less central, but they certainly are a factor that needs to be considered. The other thing that I think is important to point out here is that when you have interoperability problems, historically, we've thought about having local standards, which didn't give you the scalability, or global standards that didn't give you the flexibility. And this means that policy people have to pick between one of the two bad places, that there's no good place to live. And so the hope is that things like incremental standards actually unlock the policy process, because what they say is you can have both of these things simultaneously, you don't have to pick.
We have time for one more question. Is anything ever lost in the context of military systems by instituting interoperability? So you argue against yourself. Is there any downside here?
Is there any downside? I think there are always security concerns that are worth highlighting. As soon as you start to share information, it gives the other party more information about what you're doing, the kind of information you have, which could create vulnerabilities. I think that would be the first thing comes to mind. I'm sure there are other good answers to that, but I'm not sure I'm coming up with
I appreciate you trying. So with that, I'm going to thank you again for the great presentation and thank everyone for their attendance and the great questions we got here today. We're going to post this recording online as soon as we can. You can find all of our webinars and podcasts, including the whole Tech 101 series on our YouTube channel at Emerging Tech ETI. Subscribing to the channel will keep you up to date with all of our latest content. And if you have feedback about this Tech 101 series, especially topics you'd like to see us cover in the future, please email us at eti@ndia.org. I want to take this opportunity to highlight some upcoming products and events coming out of NDIA and ETI. We've got reports that we've recently released. Coding the Future is a report that we did in conjunction with Carnegie Mellon Software Engineering Institute and the Undersecretary for Research and Engineering. It talks about defense software R&D, and Investing in the Future is an analysis of science and technology funding trends over the last couple of decades. That's the first in a series of budget analysis reports that the ETI team is working on. Future reports coming out later this fall. One is a follow-on to our hypersonic supply chain study, which is on directed energy supply chains, and one based on a workshop that we held in San Antonio, Texas, at the NDIA Science and Technology Conference on how DoD and industry can work with minority serving institutions. So if you have any comments, questions, suggestions for topics you'd like to see us dive into and do reports on, please send us an email at eti@ndia.org. In terms of events, upcoming NDIA and ETI events, the FUSE Future Forces Capabilities Conference down in Huntsville is September 25th to 29th. Registration is now open. There is the Women in Defense Conference, which is right here in town in Arlington, Virginia, September 26th. Our next Tech 101 is on 5G. That'll be October 12th. And then in November, December, we've got high energy lasers and high powered microwaves lined up. For more information on these and all other NDI events, please visit the NDI website and the calendar of events page. I also want to preview 2 short courses that we're doing in conjunction with the Potomac Institute. Coming up on September 14th is one on venture capital, to get some insight on how venture capital works and how it's interacting with the defense system. And then one on effective science and technical communications, like the kind of communication we saw here today. This is a course run by Stony Brook University, the Alan Alda Center for Communicating Science there. We're going to be running that as a virtual course on October 19th. More information and registration information will be coming soon on the NDI website. And to join our mailing list, please contact us at our website, emergingtechnologiesinstitute.org, or email us at that email address. Thanks again to our speaker today, Jessa Lee, and thanks everyone for joining us at ETI's Tech 101 series.